Process of elimination, I have to be right about the next speaker in the XD Award, Trojan Express Network. John Maringer is going to be the presenter. He's the lead system administrator at USC's High Performance Computing and Communications Group, which provides large-scale computing infrastructure to the university research community. He has over 10 years' experience building and managing large compute infrastructures numbering in the thousands of nodes in both industry and academia. So, John, thank you. Take it away.
Last but not least, I guess.
Right.
We screw it back in. Okay. Okay. Yes, so I'm talking about the Trojan Express Network, or 10.2 network. And the naming of this is a little bit funny because 10.2 is an old code for access available, or your channel is clear. If you guys remember, like 1040 or 1020, that kind of stuff. So yes, I'm from the Center for High Performance Computing and Communications. We provide resources to university researchers at USC. Kind of our two main areas that we have, or two main resources are our Linux cluster, which is a little over 2,600 nodes. And in the last supercomputing top 500, we ranked number 60 in the world, so we're pretty proud about that. And we were number 6 in US academia. So, and then we have about 2.2 petabytes of total storage in our data center as well. This place is shared by different researchers. We have 3 different campuses. There's the University Park campus, which is our main campus, and we have a health sciences campus. And then we have in Marina Del Rey, the Information Sciences Institute is located. Kind of our problem is that research is becoming even more data and compute intensive, especially in areas like genomics. We're seeing that, like half of our storage that I mentioned is pretty much genomics data. Researchers need reliable high performance connections to large scale computational facilities. So that's like us and also the other national compute resource centers or computing centers. Another thing that's kind of maybe unique to us, but other places as well, we have the cinema school, and which is going totally digital, and the size of large visualizations require hundreds of megabits or gigabits. So for example, like 4K video, which is basically your movie screen size, is compressed as 200 megabits. So that's kind of your low end, but uncompressed, that goes up to 8 gigabits. So you can imagine getting several people trying to transfer large film screens or films around can clog up all your pipes. So, and our current campus networks kind of were designed for general purpose internet. Our campus infrastructure, like mostly we have a 1 gigabit connection to a lot of our buildings. And that's not big enough for a researcher who is doing genome sequencing where they're spitting out terabytes of data every day. The other thing is with students on campus mixing research traffic with sort of your commodity internet, you get weird spikes. It kind of can cause problems for your researchers. So you get very unpredictable traffic patterns. And also putting in firewalls to protect the campus sometimes interferes with legitimate research that people are trying to do. So our solution is deploy a parallel network which is targeted to specific researchers who actually need the bandwidth. And to do that in a cheaper way, we're instead of buying very expensive routers, we get cheaper high-end network switches and use software-defined networks like OpenFlow to control the switch. So this is kind of, the Trojan Express network is a build-out across the campus and to other research networks. So far, I don't know if you can see this. So far we've purchased a big router here, our Science DMZ. We've connected into Scenic and through Scenic to Internet 2. Right now we're working on connections to the University Park campus. Our data center is actually slightly off campus. It's about a half mile away. And then the Information Sciences Institute is about 12 miles from our data center, and the Health Sciences campus is like 10 miles away. So this will all be fiber, and we're looking at starting out with 10 gigabit connections as a minimum, and maybe 40 if we can get good deals, basically. So far we've done a couple of tests on the network just to see what kind of data we can get pushed through it. And so the first one, I'm just going to go through all these. The first one is a test between us and Clemson University in South Carolina. So we've connected through them, going through Scenic to Internet 2, and it's 100 gigabit across all the way, which is shared actually with other institutions. But to us, it looks like just one VLAN. It looks like one local network that has a very high latency and is very fast. So the physical path you can sort of see here, it goes along this southern route through the United States normally. One interesting thing about this is not knowing exactly how your network looks, you get sometimes weird things. So when this was first constructed, we actually went from Los Angeles up to the Bay Area, which is where the main Scenic Internet 2 exchange point was. And then we came back down to Los Angeles, and then went across the United States over to Clemson. A couple months after we set this up, though, they had another point in Los Angeles, and so we were able to ask them, can you reconfigure the VLAN and start us just straight from Los Angeles, which they did. So the bandwidth test we were doing, there's a 72 millisecond round trip between USC and Clemson. It's 100 gigabits. At USC, we set up an OrangeFS cluster, and OrangeFS is a parallel file system. So it was split across 12 different machines, each with 10 gigabits. So in theory, we could do 120 gigabits if we were able to max out all the machines. And then at Clemson, they had their file clients. Initially, we ran a bunch of tests using what's called Nuttcp. There's several other network testing tools out there, like iPerf or NetPerf. We kind of like Nuttcp. And then Clemson was doing file copy. After we were done testing the link, Clemson was doing file copies from their machines into the USC OrangeFS cluster. So one of the things to be aware of when you're doing a long distance network with a high latency, or what they call long fat networks, is you have to have enough memory set aside on your servers and on your clients so that they can handle all the data that's coming through. The biggest problem with these networks with high delays is if you lose a packet, TCP is going to back off. And so your window of data that's being sent across the network is going to shrink back and then slowly grow and then drop back. So we did some testing. We started off with a 90 megabyte buffer size, and then we did some additional testing and sort of bumped these up. So these values, oops, go back. These values here, these are our Linux settings on what the actual bytes were. So this is like the maximum receive buffer that Linux will allocate. This is the maximum write buffer. These are settings that it'll start with, so it'll start with these buffers and grow up. One other thing is we use a different congestion control algorithm. So normally most TCP by default uses Reno, which has an additive increase as it makes your window size bigger and bigger, and then it's an exponential decrease. So you'll slowly grow up, and then if you lose a packet somewhere in there, it'll drop back and start transmitting at a much slower speed. So yeah stands for yet another high-speed TCP algorithm. There's several out there. And one of its major, I guess, differences is that it doesn't back off as quickly. So it's more conducive to loss. And actually, when we did this experiment, we found out about a month later, because we were seeing some packet loss across this link, and it turned out to be that there was an issue with the software that was on our switch. It wasn't doing proper forward error correction, so it was dropping packets to the switch itself. And we've since corrected that as well. So, and then the other thing is, if you're on an Ethernet network, you want to do jumbo frames so that the layer 2 level you're sending things in bigger chunks. So this here on the left is the bandwidth in gigabytes per second, and the different colors are flows going from different machines. So we started off with one machine here, which is in the blue, and this is over time. And then we jumped up to 12 machines, which we were confident that we got that maxed out. And as you'll see, this first one is 12 machines here. And then we went, we got that reading, and then we said, well, let's decrease that a bit, and let's try 10 machines. And we tried 10 machines, we actually got a higher throughput than with 12. And then we decreased that, and then we went to 9, and 9 actually turned out to be the best. And the reason why we think that is basically the congestion. So if you're running all 12 machines at full speed, you're going to try to send 120 gigabits, but you only have 100 gigabits available, theoretically. And so the congestion will cause all of the machines actually to do more poorly. So that was kind of an interesting finding. And then this is a chart. Clemson did a whole bunch of different tests looking at different numbers of nodes, number of processes per node, transferring different 1 gigabyte files across. And the best they found was actually using 8 nodes and 16 parallel transfers going on at the same time. And the 37 gigabits per second, which is probably about half what we got before, is understandable because they're actually reading and writing things to disk, whereas our Nuttcp stuff is just sending sort of random memory across to maximize the link. And since this link is up, we actually do have some production usage. So USC and Clemson have sort of an exchange agreement where we store each other's data. And so there is the Digital Repository Archive, which has video from the Shoah Foundation being stored over there, going across this link. They just set this up recently, and they have these, they're like EMC storage boxes, but they have to do some tuning to achieve the full bandwidth that's available to them. And then also, kind of luckily, National Lambda Rail shut down on us. And so we had 2 1 gigabit links going between us and Clemson for all of our academic data for disaster recovery. But we were able to migrate this over to the Scenic Internet 2 VLAN in 1 week. And the really impressive thing actually is we asked Scenic for the circuit to get set up, and 2 hours later it was done. So that's pretty, to us we were shocked. It was like, oh, we figured it would be weeks, but it took 2 hours. So mostly internal was most of that time. So the next experiment we tried was putting in a transparent firewall. We were working with Fortinet, and our switch that we use is Brocade. And Fortinet doesn't have, or at that time didn't have a 100 gigabit connection. So we attempted to put together a Fortinet firewall and take 10 individual connections and bond them all together into what's called a lag. And so it was very similar to the copy test that we were doing with Clemson. Is we have the USC machines would be sending data to a machine over here in Clemson, and it would go through the Fortinet firewall, hit the USC Brocade switch, go across our 100 gigabit, and then to the Clemson side. One thing that happened though is this actually was kind of a bit of a failure because all of our traffic was getting dropped, and we couldn't figure out why. And what it turns out is when you put together 10 different links into one large link like that, if you have a transparent firewall, the data that goes across, say, the red link, when it goes this way, when the return of the acknowledgments come from Clemson, they have to go across the same link. And they weren't. They were going across like the blue connection. And the reason why that is because all of this stuff is done in hardware, and so the different blades on the firewall are not sharing data as to what flows are going through them. So although it was a failure, actually, Fortinet and Brocade were very involved, and they went back to their labs and actually have put together a new setup where they have a 100 gigabit link or 4 40 gigabit links. And so we're looking to probably retest this later this year as well. And then at Supercomputing 13 in November, we were doing another WAN test just to see how this could be used from 2 different locations. So we had our existing setup between USC and Clemson that I described before. We have several machines with 10 gigabit links and the 100 gigabit connection that was already there. And then at the Supercomputing conference on the exhibit floor, we had 4 different institutions put together, or we put a server at the booths of 4 different institutions, each with a 10 gigabit connection. So USC, the Internet 2 booth, the Clemson booth, and Omnibond, who's the maker of OrangeFS, all had a 10 gigabit connection. And so the path from USC was traveling around the south route here, And here is Denver, where SC13 was. And so everything was going fine, but then all of a sudden there was congestion between the Los Angeles and Denver connections on Internet 2. And, well, there was an institution that we shouldn't name, but it ended up being Caltech. That was also running bandwidth tests at the same time. And so it was kind of funny because all of a sudden our stuff stopped working, and we were like, what's going on? And then finally we found out what Caltech was up to. We put in a request with Internet 2 to reroute our path. And so instantly they changed our path to go across this northern route. And so this is kind of like an example of when you have these software-defined networks, you can reconfigure everything. And we didn't have to do anything. None of our configuration changed. They just made a change on their end, and then instantly, all of a sudden, we started seeing higher bandwidth across the link. So, and this is a graph that Clemson gave to us, which is similar to the other graph. The different colors here are different machines and how much data that they're pushing. And this is the throughput. And on the bottom here is time. So you can see we calculated about 30 gigabits per second from SC13 across the 4 booths, and then USC was doing about 40. So we're somewhere in between the 70 to 80 at optimum times. One of the other nice things about this is OrangeFS actually discovered some bugs in their code for when they were doing these high-speed tests, and were able to develop some improvements as well. So, and then kind of the future work for 10.2 is we've just ordered or about to order some new switches. We got a bunch of quotes in, and these are going to be the campus switches, which will connect our data center with the different campus networks, and we'll be setting up connections into the research labs themselves. And we're actually looking at our SDN software setup. We're going to use Open Daylight, it looks like, for our initial test. We'll come back and do the firewall test again. And then we're also looking to set up 100 gig connections within California. ISI has a group called Deter that's actually doing some work with Berkeley. And so I think that's probably going to be our first candidate for connecting them. So, I sort of already talked about this, but yeah, the new switches are going here and here and here, kind of thing. So, and I don't know, that's it. Is there any questions about anything?
You made me depressed. We just got 10 gigs.
Oh. Well, maybe I should write a song about it then. All right. Oh, sorry. I think it's. The question is basically why SDN helps and how it helps. So one of the things about SDN is it's kind of at the layer 2 level. So a lot of networking is at layer 3, where you're doing a lot of routing infrastructure. So if you want to change things around, say I want to connect this lab to this lab, and it's going to go over our regular routing network, the routing can get complicated at the layer 3 level. And so usually you have to buy routers that are basically, you have to buy a router which basically is like a computer within it and has a lot of high-speed networking gear in it. So by doing it with SDN, you can kind of save money by buying a cheaper switch and then having it program that switch for you. So it's kind of a cost savings thing, but it also gives you sort of the flexibility like we saw when we were able to change paths from different routes. Like even when the first scenic path was going from up to the Bay Area and back, they made that change. We didn't have to change anything. And that's all kind of like at the lower level that the software-defined networking stuff handles. So that makes sense. Anyone else?
So you basically look like you're on a VLAN the whole time?
Yes.
You're running everything at level 2 as far as you know?
As far as you know, it looks like, our Clemson machines, or the machines of Clemson and our machines, they look like they're on the same network, as far as you can tell. The only thing that you'll notice if you ping between machines is you'll just have a much higher latency between them.